Hi, my name is Amanda Weinstein. I'm an associate professor of physics at Iowa State University, and it's my great pleasure today to introduce Professor Kate Scholberg. Kate is an arts and sciences distinguished professor of physics at Duke University, where she studies topics in both astroparticle physics and neutrino physics, including neutrino signatures from core collapse supernovae. She also plays key roles in a diverse set of experiments, including Super Kamiokande, Coherent, and Dune. That last is how I know her. Kate?
I was charged with talking about core collapse supernovae, which actually has many aspects, but I'm going to, in only 15 minutes, just talk about the low energy neutrino flux, which is what I most know about. So when you have a core collapse star, actually, whether or not there is a supernova, almost all of the gravitational binding energy goes into neutrinos of all flavors in the energy range of a few tens of MeV, and that's basically because neutrinos interact so weakly that they can make off with all the energy. It's neutrinos of all flavors and antineutrinos. It's mostly nu-nu-bar pairs. And the timescale is actually determined by the diffusion timescale of the neutrinos out of the core, and it's tens of seconds. So here's a nice spectrum of the steady state neutrino flux, the so-called grand unified neutrino spectrum at Earth. And there are actually supernova neutrinos in here. There's the diffuse supernova neutrino background in the range of around a few tens of MeV. Now what I'm actually going to talk about here is the core collapse. So that actually comes from the core collapse, all the core collapses that have ever happened over the history of the universe. However, during a nearby core collapse around the Milky Way distance or a bit farther, at Earth, the supernova flux can increase by orders of magnitude. At the center of the galaxy, it would be 9 or 10 orders of magnitude. So it's a huge transient burst in this energy range that we're thinking about. And the information that we're after, both for physics and astrophysics, is in the flavor and energy and time profile of the neutrinos that arrive at Earth. And so here, this is just a picture of some plots of the top plots are luminosity as a function of time in different time eras. This is 50 milliseconds. This is about a second. It's on 10 seconds on the right-hand side for different phases of the core collapse and then the subsequent explosion. And the bottom 3 panels are the average energy of the neutrinos that come out. And imprinted on this flux are the phases of the collapse and the subsequent explosion. You get an increase of electron neutrinos coming from the protons and the electrons getting squeezed together to make the neutrons of the neutron stars. That creates electron neutrinos. That's the infall neutrinos. There's a little notch that comes from a time when the neutrinos are actually trapped, which is a kind of mind-boggling thing, that neutrinos can be trapped. There's a bright spike neutronization burst when the shock hits the neutrinosphere and neutrinos are free to stream. Freshly created NUIs are free to stream away. In the mid-time scale, you can see signatures of the explosion, especially in the electron neutrino flux. And then finally, there's a cooling. This is actually where most of the energy loss occurs in the all the flavors of the neutrinos decrease and cool over about 10 seconds. And it can go as long as hundreds of seconds as well. Let's see, and here's just some examples. This is another visualization of the flux as a function of time and energy in the 3 different flavors. Nu X refers to all the heavy flavor neutrino flavors, nu Mus and nu Taus and their antineutrinos. And you can see all the action is happening over about 10 seconds and a few tenths of MeV. There can be other exciting signatures. For example, if a black hole forms, which may result in fact, no explosion, there's a sharp cutoff of the neutrino luminosity. And that you can see that reflected in this last pattern after an initial increase in energy. So that would be a cool signature. There's also multi-messenger signatures as well, including gravitational waves, and of course, all the electromagnetic wavelengths for the subsequent explosion. This is an example of a model in which there's also a gravitational wave signal. And here you can see the time scale relative to the bounce. There are neutrinos. Actually, there's an uptick of pre-supernova neutrinos before the collapse that actually could be a true supernova early warning. Here is where the collapse happens. The blue here is a gravitational wave signal. That is, there are quite large uncertainties in what that will look like. It's not like a binary in spiral, but there's very likely some excess power and gravitational waves as well. And then all the electromagnetic fireworks happens later. It can be hours, it can be even as long as days, depending on the nature of the envelope of the star. And so the prospects for what we can learn from a galactic supernova burst are, it's enormous, or nearby supernova burst. There's an enormous amount of astrophysics, understanding how the core collapse. You can see what's happening from deep inside. You can see the cooling of a neutron star. There are also potentially interesting quark matter formation, very other interesting phenomena you can see imprinted on the signal. There's also neutrino physics to be had. Neutrinos change their flavor, and we have some prospects for learning about their mass spectrum as well. So there, and other signatures of new physics could be present in the spectrum. And all of this information is in the flavor and energy and time structure of the burst, and the more we know about the progenitor and the collapse from gravitational waves and photons, the better we can extract neutrino physics. And the more we get laboratory information from neutrino physics, the easier it will be to extract astrophysical information. So it's kind of a virtuous cycle here. And then I'll say a little bit at the end about the early alert. So how do we detect these neutrinos? So I don't have time to go into all of the details. There are many interesting experiments, detectors running. These are the main categories. I'm going to talk about water, scintillator, and argon, for which you can get very large underground detectors, and there exist some, and there are many planned for the future. The current best supernova detector is Super K, which is a water Cherenkov detector. It's actually the only instance, Super K is the only instance of a large water Cherenkov detector. This is where the particles that result from neutrino interactions, the charged particles, create Cherenkov light when they're going faster than c over n in the material, and you get a directional ring. And this is actually very important for supernova neutrino detection, in that when you have elastic scattering on electrons, the electrons remember the direction in which they were kicked. And so that allows you to actually point back to the source of the supernova. Although that is actually a low cross-section compared to this main interaction, which is electron antineutrinos on protons. This interaction forgets where the neutrino is coming from. It's almost isotropic. Nevertheless, in a detector like Super K, using the directionality of the Cherenkov ring, it should be possible to point back to the source to some degree. So here's a picture of Super K. It's 50 kilotons of ultrapure water underground, famous for other things such as Nobel Prize for atmospheric neutrinos and solar neutrinos. It's a volume of ultrapure water with instrumented with phototubes for the Cherenkov light. It's about 1 kilometer underground to be shielded from cosmic rays. Almost all of these detectors have to be underground to get rid of cosmic ray background. The next generation is Hyper K, which should be turning on sometime around 2028 or so. And the first one of these, which is about half, almost 200 kilotons. And this kind of detector would see, where Super K would see about 10,000 interactions, mostly electron antineutrinos, Hyper K will see something like 100,000 interactions. So an enormous signal from a 10 kiloparsec supernova. There are also even bigger detectors, more mass, like IceCube, which is known for looking for observing extremely high energy neutrinos, so PeV scale kind of neutrinos, where the resulting tracks create kilometer scale patterns in the photosensors in the ice. Supernova neutrinos are only tens of MeV, and you might think, how can these detectors with sparse phototube strings, how can they see those events? And the answer is that they are able to, rather than observing neutrinos one by one, they're able to see an overall glow in the ice by tracking the single photon hits from the phototubes all at once over the 10 seconds of the burst. And this enables a very nice time profile measurement of the neutrinos in a supernova burst. And actually, very good timing is possible, although it integrates all the energy. It's not an event by event kind of thing. I can say a little bit about scintillator detectors. These are, there are several instances of kiloton scale underground scintillator detectors. These are made of hydrocarbon, so carbon and hydrogen. mineral oil type detectors and that are organic compounds that emit light when excited by charged particles. These are also, due to their high free proton content, sensitive primarily to electron antineutrinos, just as the water detectors are. And what they see is the light resulting from the positron and also sometimes the capture of the neutron or the positron annihilation gamma, as you can see by Compton scattering in the detector. And there are many examples of these kinds of detectors worldwide of the kiloton scale.
4-minute warning.
Okay, so liquid argon, this is actually what I've been working on personally a lot, is detectors made of argon, which are fine-grained trackers, and these are in contrast to water and scintillator, which are sensitive to electron neutrinos. These are sensitive to electron, instead of antineutrinos, they're sensitive to electron neutrinos by this interaction, and you can track the final state products in great detail. And DUNE is the big US 40 kiloton project sensitive to this component of the flux. So it's really complementary to the water detectors. Okay, so you don't have to look at all the details on the slide. This is the summary of the supernova neutrino detectors that are online now and will be online in the near future, or perhaps the next decade, are the ones in yellow. Currently, there's a galactic sensitive sensitivity primarily to Nu bar. For the future, we're talking about much bigger detectors and also broader flavor sensitivity. This is the number of events here meaning number of interactions expected as a function of distance. Is just 1 over r squared. If you go out as far as Andromeda, you would expect maybe 1 interaction from observed in super K, but in hyper K you might get a dozen. And you want it all. You want all the flavors. This is really not a competitive game. A lot of neutrino experiments are competitive in other physics regimes, but for supernova neutrinos, you want as much as possible. And what you actually can do if you get all the experiments together is an early alert. And we've had this actually for some time. It's called SNEWS. It's funded by NSF, Supernova Early Warning System, where the idea is that if you want to get a fast alert out to the community, now individual detectors will tend to be plagued by backgrounds making false alert bursts, but if you want a high confidence alert, you can require a coincidence of bursts in different detectors. The system's been running now for more than 15 years, automated since 2005, and it's something you can go to snews.bnl.gov and sign up for the mailing list right away. And we're actually currently in the middle of a massive upgrade of all the infrastructure and adding capabilities. And one of the capabilities that SNEWS 2.0 is going to add is better pointing. So you want to be able to point fast. So here's a plot here showing how much time there is racing the shock. When does the shock break out? And it can be anything from 10 minutes or so to even a day or two, something like that. And we have different ways of doing that. As I mentioned, a detector like Super K and actually also DUNE will be able to point using anisotropic interactions themselves, where the products remember where they were kicked from. We can also use timing to triangulate, which is not likely going to be as good, but is something that can be done with low latency. And this is a major topic that SNEWS 2.0 is working on. Okay, so here's what you need to know. That's what I say at the end of my lectures, so the students will listen to my summary. So the key points are quark collapse neutrinos, 10-second prompt burst of all flavors and a few tens of MeV range. There's a range of current and near future detectors with galactic sensitivity, sensitive mainly to Nu bar, only 1 of the flavors. Pointing is maybe 5 degrees from Super K, good timing from IceCube. The SNEWS network is waiting. In the future, we will expand much bigger statistics, much richer flavor sensitivity, better pointing, and multi-messenger prospects. So I will stop there.
Thank you, Kate. That was a great overview. We have a lot of excellent questions in Q&A, but I think we only really have time for one. So the question that was asked by one of the attendees is, where in the star, from which region of the star are we actually observing the pre-supernova neutrinos? Where do they come from?
Oh, the pre-supernova neutrinos. Oh, so those are coming from generally later state, like the ones that actually happened before the core collapse, where you get an uptick. I think a lot of those are probably occurring from the layers around the core, there's silicon burning, there's various nuclear reactions. So I can point to references on that, but they're not coming from the actual iron ash core. They're coming from higher layers, but there's different components of them as well. And those, unfortunately, are probably only observable within a quite short radius, maybe only out to, probably out to Betelgeuse. We could probably see pre-supernova neutrinos from Betelgeuse, but probably not much farther than some maybe kiloparsec or so, even in the next generation